Before we start, I'd like to first remind people that following the Bowie Lecture is the Nye Lecture. So we have 2 hours on the cryosphere, a special for this AGU. I also like to remind everyone that the geodesy reception is at 6:30 tonight in the Marriott, I guess, one of the Golden Gate rooms, B2, I think. Well, welcome to the Bowie Lecture, and I think it was Mike Watkins several Bowie Lectures ago, I can't even remember now, who said that geodesy is fun. Maybe I'm paraphrasing. Geodesy is fun because you get to really work in so many different fields. And I think we've been exploring that pretty systematically over the last few Bowie Lectures, and this one's no exception. Our speaker tonight is got his degree from the, I'll see if I can say this right, École Centrale. And he said, Eric said that anyone French would know who this is, and anyone not French wouldn't. And he received his PhD from USC. He has several advanced degrees, in electrical engineering, aeronautical engineering, and astronomy. Eric Rignot's been at JPL for the last 20 years or so in the radar science group. He's been studying glacial ice, sea ice, and glaciology almost exclusively for the last 10 years. And he moved to UC Irvine only about a year ago. And with that, I'd like to welcome Dr. Eric Rignot.
Change, and this is a very hot topic. This is a topic where publications come out almost every week and change a little bit our view on things. I'm going to start with a description of the prior state of knowledge, which only goes back to a few years. What we can easily see using geodesy techniques for the most part, and I'll present some summary results on the mass balance of Greenland and Antarctic ice sheets and the impact this has on sea level rise. And I'll finish the presentation by mentioning, at least on my own view, I have this blinding light in front of me here, what I see as the challenges for the future and some conclusions. Studying the ice sheets is a formidable challenge. The Antarctic ice sheet is 1.4 times the United States, as big as Western Europe, with about 15 centimeters of water falling on it every year. And we want to find out if that area is growing or shrinking with time. Greenland is equally challenging. It's 7 times smaller, wetter. But satellite techniques have really opened a new view on the evolution of these ice sheets that could not be possible on foot because of the scale of the problem. The annual turnover of mass on these ice sheets is about 6 millimeters per year, so you see that it's the sea level rise of about 3 millimeters per year right now. You see that there's a lot of mass turnover in the ice sheets. Only a small changes in the ice sheets could have a big impact on the current rate of sea level. And there's enough ice locked up in these ice sheets to raise sea level by another 60, 70 meters. as a glaciologist and as many of my colleagues, we're not so much concerned about the little trickle of 1 millimeter per year sea level rise that we're observing today. We're concerned about what happened in the past when sea level rise was 50 times bigger than it is today because of rapid melting of ice sheets. The state of knowledge is that Antarctic ice sheet is likely to gain mass because of greater precipitation, more evaporation from the ocean. And Greenland is likely to lose mass because of increase in runoff will exceed precipitation increase. This is IPCC 2001. IPCC 2007 is not so dramatically different from that. But I hope that at the end of this lecture I will convince you that these statements need to be completely revised in the light of recent results. This is a simple cartoon which shows that ice sheets form from a densification of snow into ice, which deforms under its own weight and reaches low elevation where it can melt, produce runoff, rivers, or it can reach the ocean and form what we call floating ice shelves, which eventually break off into icebergs. So it interacts with the atmosphere, it interacts with the ocean also, because the floating part of these glaciers is interacting with the ocean. In reality, the flow of the ice is quite complex. It's similar to what you have on an hydrological basins. The ice is organized into these rivers of ice, which we call ice streams and glaciers, which conduct the major part of the ice accumulated in the interior. Melt at the surface, it produces these beautiful lakes at the surface of Greenland when there's enough meltwater being produced, and these lakes eventually penetrate all the way to the bed through moulins or crevasse networks and have a big impact on the flow of ice. For glaciologists, water is the lubricant of ice sheets. It's a very important part of the glacier landscape, and as you can see here, the important part of ice sheet flow is what happens at the bottom, and that's the part that we can't see because it's much more comfortable to do field work at the top. So if you do field work at the top in the middle of summer in Greenland, you need scuba diving equipment. If you go to the northern part of Greenland, you don't use mountaineering boots, you use fisherman boots because there's a lot of melting even in the north of Greenland. In the Antarctic, this is a picture from Pedro's Varka on the Larsen ice shelf. There's a big river of meltwater here shooting off into the Weddell Sea, which shows that there's also melting in the Antarctic ice sheet. Now, about 12 years ago, I was still a glaciologist in training, and we stumbled on this data from Prasad Guggenheim with Ken Jezek, and Ken immediately saw the importance of this result. This is Petermann Glacier flowing from left to right, and this is a thickness profile. This is the thickness here, and this is the surface elevation from laser. And this is the transition boundary, the grounding line between grounded ice and floating ice. You see the bottom crevasses on the floating ice, and a tremendous change in thickness as the ice becomes afloat. This is not due to plastic necking. This is not due to an adjustment of velocities across the boundary. This is due to the melting of the ice by the ocean underneath. And you see that in about 20 kilometers, half of the ice coming from these glaciers is melted down by the ocean. At the surface, you have a turnover of mass about 1 meter. And if you look at conservation of mass on this floating ice shelf, you find that the melt rate from the bottom is as high as 25 meters per year. So we have an order of magnitude more melt happening at the bottom of these floating extensions than at the top. And this has, of course, very profound implications on the evolution of ice sheets. There's several scenarios of melting underneath an ice shelf. Dense saline water is formed by formation of sea ice and creeps down to these grounding lines. The continental shelf is slanted towards the interior because the ice sheet is depressing the ground, and it can melt the ice deep down, and the fresh water will race through the water column, eventually form marine ice or escape the cavity. It can also have a direct inflow of intermediate depth water into the ice shelf that produces melting, or you can have effect of tides and coastal currents along the ice front. What drives the system is also that the melting point decreases with depth, about 0.75 degree per kilometer. And in the Antarctic, a lot of these grounding lines are 2 kilometers down. So it's a lot easier. You gain an extra a degree and a half thermal forcing deep down to melt the ice. So this makes this whole process very efficient. All the ice sheet models, even those which we all criticize so heavily following the IPCC report, they all indicate bottom melting is a crucial element of ice sheet evolution. This has always been known in glaciology that these interactions are extremely important. But we don't have enough information on melt rates. We don't have much of any idea how these melt rates could change with climate change. Now, there's 3 different ways currently to look at the mass balance of ice sheets. The first one, you want to see if the ice sheet is growing or shrinking. It's like looking at your sun. You want to know if it's growing or shrinking. You measure its height. And these techniques have been deployed since the 70s, so they have an history behind them, even though most of the accurate measurements started around the 1990s. They used radar altimeters started from the ERS. The NASA Parker program with the ATM, airborne topographic laser mapping, started in the 90s, and this was followed by ISAT in the year 2000. Altimeter can detect changes in height of about an order of a meter. Laser improves that by an order of magnitude to about 10 centimeters. These techniques measure the volume change of ice sheets. If you want to convert that into mass, you have to know at which density these changes are taking place. And there's a lot of uncertainty on whether these changes are snow or ice. The challenge of this technique also is to have a very dense sampling of the area to make sure you capture all the changes. In the 2000, a new technique came along, gravity survey. And the advantage of this technique is that it measures directly what you want. It measures mass. It measures mass change. It does not depend on the density and ice thickness or ice velocity. You directly get this noble quantity, which is gravity. And in the Antarctic, Grace probably, with the paper by Velikania and Moore, provided the first modern and reliable estimate of the mass balance of the ice sheet. And this indicated a mass loss of the Antarctic ice sheet. There was a lot of results published on the Greenland ice sheet as well. The current disadvantage of these techniques is the low resolution. It's not a fundamental limitation of the technique, but it's currently limited to 200 to 400 kilometers, so you cannot resolve the details of glaciers and individual basins. And especially in the case of the Antarctic, you have to make some correction for the post-glacial rebound. Now, the third technique is to do the mass budget, basically compare what comes in with what comes out. You need to know what comes in. This is an accumulation map from Michiel van den Berg. You need to know what comes out. You need to have the velocities of all the glaciers, and you need to know how thick they are. So you need a lot of data to do this technique, and you're comparing 2 big numbers, what comes in, what comes out. And prior to the advent of satellites, it was almost impossible to use this technique to say anything about these ice sheets because the uncertainties were too large. And even with satellites, it became very clear that in order to get an answer for the whole ice sheet, you had to look at every place around the ice sheet and not have any a priori or where changes could take place and where others could not take place. As we went along, we discovered places changing that we didn't quite expect. The glacier mass budget compares what comes in and what comes out. It relies on thickness, which we know within 10 meters from radio echo sounding. If we could have radio echo sounding everywhere, we would prefer that. But for most of the Antarctic, we don't. And we infer ice thickness from hydrostatic equilibrium and measurements of surface elevation with altimeters instead. The speed is measured with interferometry with very high precision, so we can get the outflow. The input is snowfall minus melt when there is some. It's known, actually should be 5 to 30%. And we can determine with these geodesy techniques mass balance within 5 to 30% depending on the nature of the basin. And this is here an example of velocity across Pine Island, and you see the thickness profile. This is how you measure the flux of ice going through that narrow gate. And you integrate all the snowfall into that basin to determine how much should come out to maintain the system in mass balance. To measure motion, we use satellite radar interferometry, and a lot of what I've done in the past 10 years used this technique. I was at JPL basically at the right time with the right tool. It's a fantastic technique, which was pioneered at JPL by people like Richard Goldstein, but only came into life with the launch of ERS in 1991. Radar is measuring the distance from an antenna to the ground. Radar interferometry measures how this distance changes with time by constructing destructive and constructive interferences between the two complex signals recorded by the antenna from the same point on the ground. So it measures the change in position of the ground with time as fractions of the wavelength, which is a few centimeters for these radars. So in terms of millimeters, it's independent of the pixel size you're looking at the ground. This is Pine Island Glacier here, flowing from south to north into this floating extension. And with radar interferometry, we operate some kind of an X-ray of this area to look at the deformation rates. The satellite is flying from top to bottom, looking to its right here. This is a ranging measurement, so we only measure the direction of flow in this direction here, perpendicular to the flow. It's only a one-dimensional measurement. You see the fast flow of the ice stream. You see the tributaries, which are very difficult to see here. And the density of these contours here is directly a representation of the strain rates of the ice. And I have to tell you, I've been generating interferograms like this for the past 10 years, and I never get bored of looking at that stuff. This stuff is absolutely fantastic. Now, there's even better than that. If you have several interferograms, you can difference them, and you can look at the short-term variability in deformation of the ground. And this is an example on the same glacier where we difference two interferograms, and what you see is the signal that's not constant with time. So the flow of the ice disappeared, the main flow of the ice disappeared here. We can see little bumps here corresponding to the ice going up and down because maybe some subglacial light discharge in between these two epochs. And then we see the transition from the grounding ice to the floating ice. You see this narrow set of fringes here, which represents this transition. If we zoom up a little bit on this, this represents the grounding line and the transition from grounding ice to floating ice. And this zone is the flexor zone where the ice is adjusting to hydrostatic equilibrium. And in glaciology, knowing where the grounding line is like the holy grail. If you try to find it on the surface, you won't see it. If you try to deploy instruments like GPS or tiltmeters, you have to start with a very good idea where it might be. And in the past, presumed position of the grounding lines could be several kilometers in error. In the case of Lambert Glacier, it was 150 kilometers in error. So this technique not only tells us where the grounding line is, it gives us a snapshot of a large area and shows us where the ice is flapping up and down with tides. So grounding line is important because it marks the transition from contact with the bed with contact to the ocean. It's also where we want to measure the fluxes to determine the mass balance and the contribution to sea level rise. It's also an area where we can apply the assumption of hydrostatic equilibrium because the ice is becoming afloat and we can calculate thickness for the mass balance fluxes. But there's a lot of details in these maps that I just brushed aside. We're just taking the cream out of this fantastic data. You see, for example, here, this is an ice rise and these are tidal fringes. If you count the fringes from the center of this point to the outside, you're going to find less fringes. And what that means is that this is a part of the ice shelf which touches the ground at low tide and then gets off the ground, so you don't get as much deformation. And we can see the evolution of these points with time. I don't think there's any other technique than INSAR that can look at these sorts of deformation. A lot of progress has been made in Antarctic surface mass balance. For many years, we had maps of surface mass balance which were interpolation from sparse field data with sometimes unreliable accuracy or taken at different epochs. And this changed with the work of Michel van den Berg at the University of Utrecht, who produced these maps of surface mass balance which are coming from a regional climate model and which use the in situ data for verification. So it's not an interpolation technique anymore. We produce these fields. And I still remember in 1996 when Atsumu Omura told us at this conference in Zurich that he thought that the models were getting so good that someday we won't need to go to the ice sheets to measure accumulation and melt. We would be able to predict that from models. And he's a very serious guy. I was quite shocked by this declaration. But 10 years later, the models are there. They're producing incredible results, very realistic values of the surface mass balance. And you can evaluate the precision of these results by comparing with field data, 5% in the dry regions, 30% in the wet regions. And even more important results is that Michael and Monaghan et al. Determined that there is very little change in Antarctic snow accumulation in the interior in the past 25 years. Greenland. A lot of progress also made in Greenland in determining surface mass balance. And I think we're coming to closure with surface mass balance now. There was still a lot of uncertainties a few years ago. These are the results from Evan Burgess, Jason Box, and others, which shows the precipitation in Greenland, the surface mass balance, and the runoff. This is to bring things into context, which shows that accumulation in Greenland varies over the time scale of several centuries by only 10–20%. We always hear these talks in the media of increased precipitation on the ice sheets that are going to counteract the melting of the glaciers. When you vary accumulation on the ice sheet, you vary it by 10–20%. That's a big, big deal. That's, it doesn't happen in just a few days. And in fact, if you look at the trends in Greenland in precipitation, over the last 50 years, there's a trend of about 1 gigaton per year, which is very small, and not much of a trend in surface mass balance. If we look at the last 10 years, however, there's a clear trend in increased runoff and not much of a change in the accumulation, but a lot of internal variability. If you take any few years of data along here and try to put a trend, you can get anything you want. But if you look at the longer-term trend, there's nothing appealing to me that there's a dramatic change in precipitation in Greenland. And this is consistent with all the ice cores that were drilled during the Parker years. I still remember Jan Willens staring at these ice cores and saying, look at this, it's amazing. The accumulation is almost steady the whole time. This is the record of Greenland temperature in southeast Greenland over the last century. We are in this part of the curve here with very rapidly raising temperature of about 3 degrees between the 80s and present day. This period was cold. There's a warmer period in the 30s and 40s. And this is here the temperature of the ocean along the coast of Greenland. And this is, in fact, in central West Greenland. The bottom curves here correspond to the upper layers of the water, and the red curve corresponds to the lower layers. And you see that the bumps are almost present, and at the same time, the ocean temperatures follow more or less the surface temperature, except when there's great salinity anomalies. Here also we see an increase in water temperature along the coast of Greenland. I'll come back to that in a little bit. I'm going to skip that. These are results from Ian Chogan on Jakobshavn Isbrae. I still remember a colleague of mine saying, why do they study Jakobshavn Isbrae? It's been studied for so long. Nothing is happening much. That was true until about the mid-95, 96, when the glacier started to retreat very rapidly. The floating tongue retreated very rapidly. It took about 50 years for the glacier to retreat from that point to here, and 5 years to retreat from that point to here. At the same time, the glacier speed, which you see here from inland towards the ice front, doubled very rapidly, and the floating section of Jakobshavn has disappeared. This is a record of the type of thinning rates on Jakobshavn from Bill Crable and his ATM instrument. The scale here goes to 15 meters per year. This is Jakobshavn Isbrae. And you see that it propagates very far inland between 1997 and 2002. And when we look a few years later, you see that the wave of thinning is diffused inland. And this is something very important for us to try to understand the implication of these coastal changes into the inland parts of the ice sheet. And we see already with just a few years that this diffusion is very fast and very effective and goes very far inland. This was a picture taken by John Sontag during one of his ATM flights of Kangerlussuaq, which also sped up at the same time. You see all these broken debris in front of the glacier. This is the calving front. And this is the margin of the glacier, which stands out above the glacier surface, about 30 meters. It's there because the glacier used to be there just a few months ago, and it drew down so quickly. There's some pieces of the glaciers that are still attached on the side of the valley walls, as witnessed of the rapid changes in these glaciers. The type of rates for thinning measured by laser altimetry, I don't think anyone would have expected to observe something like this. This technique was designed to measure centimetric changes. On the Jakobshavn, we have 15 meters per year thinning. On the Kangerlussuaq Glacier, the thinning rate went all the way to 50 meters per year. This is an enormous rate of thinning. The picture on the left is something we published in 2006, which shows a survey of all the velocities in Greenland. And the red blotches show areas of speed up, mostly along the southern half of Greenland. This is Kangerlussuaq, Helheim, which is in Norwegian, I think it means the goddess of death. A lot of the other glaciers in Greenland have weird names, like Glacier to the north, Glacier to the south, Glacier has turned right. Or in this area here, they don't even have names. Nasty weather. We combine the velocity measurements with ice thickness and surface mass balance to calculate the mass loss of the ice sheet. And this is for the 1990s to the recent years. You see very high mass loss in 2005, which is a time where a lot of these glaciers were speeding up. And in 2006, some of these glaciers here slowed down a little bit, but they're still way out there. What we did is add some numbers for the 60s, the last IGY, where velocities were measured along the coast of Greenland by the Expédition Polaire Française, and there's also some information on satellite velocity from the SPY satellites, which were released about 10 years ago. So we have some estimates with larger error bars for the early 60s, and you see that there is a mass loss here as well. In this graph, we try to correlate the change in surface mass balance, the mass balance anomalies, with the change in ice discharge. So 0 would maintain the ice sheet in balance. 0 would be a discharge that maintains the ice sheet in balance. And you see this regression here, which is only based on a few points, but is clearly indicative of a trend. And this is not surprising, because the surface mass balance is really dominated by the runoff. And when the runoff increases, there's more melt on the ice sheet. And the more melt is inclusive of a more rapid flow. And I will come to that a little bit later. This is not something you would expect in the Antarctic. But using this, we've been able to reconstruct the mass balance of the ice sheet of the past 50 years. The blue is the total mass balance, the red is due to ice discharge, and the green is due to surface mass balance only. And the take-home message from that, which you could see already from this regression, when you see the coefficient here of 1.58, is that the anomalies in ice discharge contribute 60% more to the mass loss than surface mass balance. So the dominant component of ice sheet loss in Greenland is from glacier dynamics. It contributes 2/3 of the loss compared to 1/3 from the surface mass balance. So this is the reconstructor curve from INSAR. Now the next view graph compares that with GRACE. There's been a lot of results published on GRACE using a linear fit to the data. And now that we have a lot more data on GRACE, Isabella did something a little bit different here, where we calculated the slope over a time range of 2 years. So you smooth the fields over 2 years and calculate the slope, and how it changes from month to month. And this is the type of mass loss that you get from the GRACE data, and matches really well with the trend from the INSAR, maybe a little bit steeper on this upper part here, but very good correspondence over here. Now everyone else, when we plug everyone else, it becomes a little bit more foggy. These are the different estimates from GRACE are shown in circles, and the estimates from Altimetry are shown in these squares here. They lay typically about 100 gigatons higher than some of the INSAR and GRACE estimates. They all show a very strong trend in increased mass loss. if you ask Bob Thomas about the difference between these points and these, he'll tell you, well, you know, the ATM surveys doesn't survey all the glaciers. And where they didn't survey the glaciers, they use a melt model to calculate the mass loss. So it's not including any of the ice dynamics into the number. So by essence, this number is always going to underestimate the actual loss of the ice sheets. For the rest of the altimetry, there's another paper by Bob which compares the radar altimetry results with the ISAT results. And he found a lot of differences. Difficulties, of course, for the radar altimeter to probe these narrow channels, which are the glaciers. The fact also that the interior of the ice sheet, because there's more melt, it raises the reflecting of the horizon of the radar. And this can be interpreted as an increase in accumulation, but the accumulation is not changing. It's just the reflecting horizon that changes. And you see that very well when you compare radar with ISAT. But the other big problem of this data is that there's insufficient coverage along the coast. If you want to really capture all the changes in these glaciers, you have to have data in each one of these glaciers. And a lot of losses here, for instance, is 100 gigatons per year lost in this sector. It's very difficult to probe with the satellite altimetry technique. What causes this change? Water, lubrication. Meltwater lubricates glacier flow. If you deny that and you're a glaciologist, you're thrown out of the room. Seasonal effects, however, are small. This was already shown by Zwally. We saw that on Jakobshavn. I looked at all the glaciers in Greenland I possibly could during the summer, and we still, independent of latitude, of climate, we still find a seasonal effect of only 8 to 10% speed up in the summer. So between lots of water from the surface or no meltwater, at a little 10% push. So the so-called Zwally effect, and Jay never really signed for this being called the Zwally effect, by the way, is small. As a teaser, the Thomas effect is big. And the Thomas effect refers to glacier and grounding. And this phenomena completely explains what happens in Greenland. It completely explains what happens in Antarctica. As ice reaches the ocean, it's experiencing shearing along the sides of the embayment. It's experiencing resistance from the pinning points. It's experiencing shearing along the bed. If the glacier retreats because the ice shelf collapses, loses contact with the pinning point, or the grounding line retreats, the part of the ice upstream is going to feel that effect. It's going to feel a change in flow resistance, and it's going to be able to speed up. And it's very easy to double the speed of the glacier with this. With just retreating the grounding line by a few kilometers, the glaciers will feel that effect very, very strongly. At the same time, the glacier will get steeper because the thinning from ice dynamics will be higher here than inland, and this will help propagate the signal inland. So Bob discussed that for Jakobshavn Isbury. He showed that this was very well explaining the trend on Pine Island Glacier, and he was very pleased to hear about 6 months ago that we measured the velocity of Pine Island. It was a big speed up compared to the previous years, and it was right on his predictions. Well, what caused the Jakobshavn speed up? A key paper came out from David Holland, Bob Thomas, and others on that. They showed this is a series of a temperature along the ocean in West Greenland. Jakobshavn is about here, which shows a dramatic change in ocean temperatures just about the time Jakobshavn started to collapse. From the ATM measurements, we knew that the ice tongue must have been filling 80 meters per year at some point to entrain the collapse. And they showed with their data that the collapse coincided with the incoming of warm waters into the fjord. This is Jakobshavn Fjord here, 3 degrees above normal. We don't know very well these ice interactions, especially in Greenland. There's very few measurements. There's measurements in Alaska, which reported 12 meters per day melting in the calving faces of Alaska glaciers. We recently went in Greenland and measured melt rates, not as large as Alaska, but the thermal forcing is less, but very large melt rates in the front calving faces. What we know today a little bit better is what's happening on these big ice shelves, and this was we published this first in 2002. This is an update which compares the rate of melting close to the grounding line, not the average over the whole ice shelf. If you want to see the average over the whole ice shelf, I'll present that on Thursday. And this is the thermal forcing, which is the difference between the ocean temperature and the melting point of sea ice. There's a lot of spread in this data, but there's a linear correlation between thermal forcing and grounding line melt. And the slope is that an increase in ocean temperatures of 1/10 of a degree is going to increase the melt by 1 meter per year. So it's a very big factor. Now, this is a good switch for the Antarctic mass balance. This is a result of ice velocity survey of the Antarctic ice sheet, very comprehensive coverage of West Antarctica, the peninsula, more partial for East Antarctica, but we captured all the big glaciers. And the blobs in red represent areas of large mass loss, and the blue blobs represent areas of mass gain. So you see that we have some losses in the northern part of the peninsula. I'll come to that in a second. And a lot of losses in the northern part of West Antarctica. And in East Antarctica, there's not much of a change. Another important fact is that these losses are increasing with time, and they're increasing with time because all these glaciers here are speeding up. In 2002, Larsen B collapsed after 10,000 years of existence. These are pictures you've seen over and over many times. And this was a good time for glaciologists to look at the effect of ice shelf buttressing. And what we found on these glaciers is that they went from speed of a few hundred meters per year to a few kilometers per year. Not only they responded to the ice shelf collapse, they sped up by a factor 8. This is Crane Glacier here, which speeding up was a bit more progressive. It's still speeding up to this day. It's sped up by a factor 3. So these are much bigger changes than in Greenland. Conversely, the glaciers that are still flowing into an ice shelf, a remnant part of the ice shelf here, part of Larsen B, did not change their speed at all. Some of these changes were so abrupt. Pedro Svarka recorded the presence of these stranded ice terraces on the side of Dugalski glaciers, which were witnesses of a very rapid drawdown of the glaciers. Grace sees the same thing. It sees the same blob of mass loss centered on the Pine Island Bay area. And even for the peninsula, it can tell that the mass loss is concentrated on the northern tip of the peninsula, and there's not much going on farther south. And the numbers also are in the same ballpark. And altimetry also shows the same thing. I'm always a little bit critical of the use of altimetry to look at mass balance numbers, but this technique has been extremely useful to tell us where things were changing. You see the changes here in Pine Island Bay. You see some changes in Cook Ice Shelf and Totem Glaciers, places we did not expect to see any changes. We see changes here on these small glaciers on the other side of Pine Island, where we didn't expect any changes, and there's a lot of mass loss here on these glaciers. You see also that areas of largest mass loss here in red, brown and red, correspond to the areas of fast flow. So this is showing that this is not a change in snowfall. This is a response to ice dynamics. This change in ice thickness are occurring right where the ice is flowing fast, and it's flowing faster. One area of particular interest is the Pine Island sector, which is Pine Island Glacier, Thwaites and Smith and other glaciers here. This rests on bedrock very far below sea level. 30 years ago, Terry Hughes was standing in the front row, told everybody this is the area to watch out, it's going to come down, and for 30 years nobody really believed Terry until we had satellites to show that indeed this is the place of major change in the Antarctic ice sheet. This is a record of ice velocity from inland towards the grounding line and on the floating ice shelf from the 70s to last year. And there's different time separation here between the two. The glacier is speeding up more and more. The rate of increase was about 1% in the 80s, 2% in the 90s. It was 8% in the last 16 months. So it's not linear. This is an exponential increase in velocity. It's only a moderate increase since 1975, but this is really not moving towards any form of stabilization. This is the picture that emerges from this for the Antarctic mass balance. So this is the INSAR survey here with some points from 96 all the way to 2007. This is strongly constrained by what's happening in the peninsula and West Antarctica. East Antarctica is kind of a zero blob on the side. And these numbers with higher uncertainties are from the 70s, where we had measurements of the West Antarctic ice streams, the Pine Island area. You see this sort of very rapid increase, although we have no information here. This is the background signal that Philip Ubrecht calculated, which is the ongoing deglaciation of West Antarctica, which is about 19 gigatons per year. And here again, we look at the slope of the GRACE results. Instead of fitting a linear trend over the last 6 years of GRACE, we look at the change in slope, and you see also a very rapid increase in mass loss from GRACE data and a good correspondence with INSAR. And the altimetry results are stuck over here, and the reason for that is that they're strongly biased by the weather in the interior, and they have difficulties capturing all these changes on the glaciers. The sectors are at risk. The sectors that you see fitting in the red altimetry map are the sectors which are deeply grounded below sea level. Well, West Antarctica, we knew that. But even in East Antarctica, Totem and Cook Ice Shelf are fitting. They're not speeding up. We've not been able to detect any speed up of these glaciers. We have no idea why they're fitting right now. But they turn out to be in the sectors which are more prone to instabilities than anything else. West Antarctica can raise sea level by 5-6 meters. This glacier alone here drains enough ice to raise global sea level by 5 meters. This is a summary of the contribution of glaciers to sea level. This is Greenland, the pink dots. This is Antarctica going back to the 70s. And these are the results from Mark Meyer in his 2007 paper for the mountain glaciers. Thermal expansion has been increasing in the last few years. There's been very little thermal expansion, in fact. It goes through these ups and downs. Greenland has been, the mountain glaciers have been increasing their contribution to sea level. We see Greenland has been increasing too. Antarctica was already contributing way before the satellites to sea level rise. This is based on the numbers from the 70s. This is average, the same averages taken for the IPCC report, but the results are very different. These numbers are much higher than what you would find in the 2007 IPCC, and they're based on results that were published after the deadline for IPCC to accept publications. You see that we have a good agreement. We have almost a closure of the budget compared to the observations from altimeters. But the more important part of this is that if you sum up Greenland and Antarctica, they're bigger than the mountain glaciers. They've been bigger not for just the last few years. They've been bigger for a long time. And if you add all the glaciers together, they are bigger than the thermal expansion already. It's not something we're looking at for the future. It's already like that today. Predictions. This is the IPCC predictions. We're heading for climate 2 to 3 degrees warmer by the end of the century. And we know in the past sea level was a few meters higher when the Earth was in that climate for a long time. There was rapid sea level rise. Ramstorff, after the IPCC report, published a regression between global temperature and sea level, which predicted a much higher range of sea level for the future. And recently, Tad Pfeffer revisited that problem for ice sheets, and based on kinematic constraint, came up with a much larger number as well. So this is the IPCC curve. This is this Ramstorff curve, and this is the IPCC prediction. With a little side note, by the way, we did not include fast flow from the ice sheets, because we don't have good models to do that. Ramstorff predicts this number if ice sheets behave somehow in a linear fashion. If everything goes linear, we're going to be heading for this number. I don't think we see anything linear in these ice sheets these days. At the current rate of increase of the mass loss in Greenland and Antarctica and the mountain glaciers, we're going to get 70 centimeters by 2100. This is if things keep going as they go today. If we go to the extreme, as Tad explored, multiply the discharge of wind by 10, Amundsen sea cycle by 10, and get 2 meters. That's going to be very hard to do, but I don't think I would bet my hand that it's not going to happen. And this does not include what may happen to the rest of West Antarctica. It does not include what may happen to this whole sector of East Antarctica in the next 90 years. it might be difficult to say, oh, nothing much is going to happen. Not sure I'm doing with time. To get away from this situation, we're going to have to move to a new generation of models. And these models include higher order model, higher resolution, and data assimilation techniques. And we are coming there. There are techniques which were pioneered by Doug McHale, who is right here, derived from oceanography. We've just been very slow in glaciology to apply them to glaciology problems because we didn't have the data. Now we do, and this is showing the rheology of the running ice shelf. You see that there's nothing uniform in an ice shelf in terms of rheology. And if you really want to model the flow of this ice shelf well, you have to account for that. These are results from Ian Jordan on the Cypress Coast ice stream, which are defining the areas of high basal drag versus low basal drag. So we can capture the most important missing components of this model, which is the friction of the bed. And it's very difficult to model that, but you can infer that from the data, and as a result, start building more realistic model. We also need to move to higher order, higher resolution ice sheet models. I think some of us feel that the models that people like Doug McHale put together provides a very realistic description of ice streams. But now is a good time to explore these higher models and to see how much difference they would bring into these predictions compared to some of the simpler models, simplified models. And we can do this today because of higher computer capabilities. These are results from Eric Lauer at JPL, where he had several million elements to model the green ice sheet at 3.5 kilometer resolution. Most of the IPCC models use grid of 10 or 20 kilometers, and they can't capture ice streams. We can capture ice streams with this type of resolution. And this is a simulation of Antarctic ice flow with 10 million elements. So I think hopefully in the next IPCC report we'll have some sort of predictions from these newer models. How do we get there? We need to maintain the observation network. And I claim that we need all these techniques. All these techniques really brought their piece of element to the whole story, to the whole puzzle. One technique won't do it all. One technique will only tell you something. We need altimetry. Even if I have INSAR, which tells me that this glacier is spinning up, I want someone to measure how fast it's spinning. I can calculate it, but I really want to have the observation that tells me how fast it's spinning. It's really important. Gravity, it is the best way to determine the mass balance of the ice sheet. There's no question about that. And if we can improve the resolution and make sure we don't have this gap between GRACE and GRACE follow-on, which really is regrettable given the success of this technique. And interferometry, because ice dynamics is extremely important to characterize these ice sheets. Thickness has been a little bit left out, because we know the thickness of the interior of the ice, but the important part, the glaciers, is really poorly covered. If you look at the actual data of glacier thickness in Antarctic, you'll be amazed how little we know, especially in East Antarctica, about the thickness of the glaciers. There's many places there's absolutely no data. Or you look at the data, and as soon as they cross the glacier, there's a gap. So it's difficult to model these glaciers if you don't know how thick they are. There's going to be massive effort in ice-ocean interaction. I think major progresses have been made in terms of nailing down atmosphere ice or interactions. We really don't know enough about what's happening at the ice-ocean interaction. I think there's been evidence gathered by our community showing that these are extremely important in determining the evolution of ice sheets. And that requires comprehensive survey of bathymetry. We need to know the shape of these cavities, the ice shelf cavities. We need to know the depth of the seafloor in front of the glaciers and right behind the grounding line. And we need to know what the ocean temperature is doing near these glaciers. At present, there's very little data on that. And finally, massive efforts are needed to develop this higher order, higher resolution ice sheet modeling. And this is only a small aspect. And I have a statement here that if we don't have that, we're going to be climbing Everest in tennis shoes. As a comparison, this is the ice thickness map of Mars. It's all covered. It's getting better with time because it keeps gathering data. This satellite could work very well on Earth, by the way. The topography of the Mars polar ice cap is so good, you can buy hiking maps. You know you can buy hiking maps of Mars online? I would not hike in Antarctica with the existing topography. In conclusion, Greenland and Antarctica have contributed sooner, faster, and more significantly to sea level. And I insist on the Antarctica because in the last IPCC report there was still a big question mark on Antarctica, and I think we really have solid evidence that Antarctica ice sheet is contributing to sea level change. In fact, if you sum up the big ice sheets, the big gorillas, as Richard likes to call them, they're already bigger than the mountain glaciers, even though that doesn't mean the mountain glaciers are not important, by the way, but the ice sheets are already there. And this is all bigger than thermal expansion. 1 meter sea level rise by 2100 is very likely, without any major ice sheet runaway. Look at the numbers. Beyond 2100, it's becoming science fiction, but several meters sea level rise, I mean, it's certainly not going to go down, right? I mean, it's going to be a lot more changes at the rate things are changing. There's no need to run to the hills. This is a statement from Wally. I really liked it. But I would walk. Thank you.
We have time for a few questions. It's hard for me to actually see out there. Yes?
Eric, I agree with everything you said, first of all. But I want to add something, and that is, in your conclusions there, you mentioned that the Greenland and Antarctica have already caught up. They're already moving faster and sooner than expected. The glaciers and ice caps might be doing the same thing, but we don't know because we're not looking. Glaciers and ice caps, if some fraction of them have the same kind of marine dynamic susceptibility that you're discussing in Greenland and Antarctica, but we don't know what fraction that is. And as poor as our coverage of Greenland and Antarctica is compared to Mars, the glaciers and ice caps are even more poorly covered.
Yes.
But as you said, they're still big players.
Now, that's a very good point, Tad. And James Cogley had a very good comment about that. He said the only way to solve this is to have a graceful on top of missions. That's really going to tell us what these smaller places are doing.
Any other questions?
Yes.
Yes.
Why do you have thermal expansion lower in the research period? In your paper, the thermal expansion was lower in the research period.
The recent thermal expansion? Yeah, the ocean has been a little bit cooling in the recent years. So this estimate I got is from Josh Willish. I don't know if he's in the room, but the last few years, thermal expansion has not been as large as before. If you look at the curve of sea level rise, you know, there's all kinds of bumps and hollows in that curve, and we're in a little bump. I don't know what it means.
It's clear that in IPCC, it's well written that it's underestimated.
I'm sorry, I can't.
IPCC estimate is well written that is underestimated because the ice flow acceleration is not
Yeah.
very good.
Yeah, the IPCC estimates, they totally ignored the ice sheets. They just put it at a footprint. And believe me, the glaciologists involved in IPCC fought that decision really hard. It became from footprint to a little bit more prominent note. But it's also our fault because IPCC is based on predictions. It's based on models. And we haven't had the right type of models to do these sorts of predictions. Not yet, but hopefully by the next IPCC, which is right around the corner, by the way, we'll do a little bit better. This is changing too fast. I mean, to solve the problem, we need to slow down changes to give us a little bit more time.
We have time for maybe one more question.
Eric, glaciologists who model ice sheets have use the equations of static equilibrium, which the only acceleration term is gravity. But for these processes that you're talking about here, rapid disintegration of ice shelves, ocean swells that can cause perturbations under ice shelves that are already highly fractured, like Doug McHale has studied. Do you think it's necessary to use the equations of dynamic equilibrium, especially for these processes that have maybe short-term accelerations, but maybe you will get that whole system over critical thresholds that throw them into a different dynamic regime?
I don't know. That's a good question, Terry. I don't think we have the answer. I think the door is open now for modelers. Models exist. They maybe didn't have the capability to look at things on a large scale, high resolution a few years ago. Now they can. They didn't have the data to compare the results with in the past. We didn't have the high resolution data, the high temporal variability in ice flow, the response of the glaciers to ice shelf collapse, and these sorts of things. It's a wide open field right now. And the questions such as the one you just asked, I think these are the kind of questions that need to be answered. What kind of model do we need? What kind of sophistication in the model do we need to make reasonable predictions for the future? I'm not the one to, I don't know. I don't know the answer to that.
Could I steal the mic first? I guess we could go on talking about glaciers forever, but we have to make room for a glaciology talk. So, Eric, I'd like to present the certificate to you from the geodesy section, and I'd like to thank you very much for and I guess with that, the Bowie lecture has ended, and we'll make some